Okay, so this is my chemical program, which displays the methane molecule rotating in 3D space.
I'll be right back.
Let me just show you what it looks like first. Allow me to fix that. That's what it looks like. Here we see the carbon atom, or what's supposed to represent the carbon atom, and we have the 4 hydrogen atoms, and they're all rotating about the y-axis, and this one being stationary because of its position. So let me explain how it works. So I imported GPDraw, which is a file which is provided. It has all the various methods and constructors and other such things that will be needed for this program. One could also do this in an applet or, say, a JFrame, but for this program it is required we use GPDraw. So in main, for various reasons I had it throw an exception, my main method throw an exception, as opposed to using multiple try-catch statements. I don't exactly remember why I did that or which lines threw exceptions. Let's see which ones. There you go, thread.sleep. This method throws an exception, java.lang.interrupted exception, something along those lines, because it's a thread, and those are rather tedious to work with. So I don't really like try-catch statements, so it was made a bit more sense to use throws exception in this case. But otherwise we would not normally do that. So to start the first line, this one right here, what it does, it creates a new drawing tool which will be used to draw, and it also creates a new sketchpad on which to draw, and that is the new sketchpad 700 by 700. As indicated by its constructor, it's 700 pixels by 700 pixels wide by default. This next line declares a two-dimensional array in which I'm placing 4 points, namely the 4 hydrogen atoms, one of which is stationary. As you can see, there are 4 points, and the other dimension, 3, is the number of dimensions, because each point has 3 dimensions that locate its position. Theta here is the angle of rotation. Every cycle I increment theta and then recalculate their positions to determine where they would be in 3D space. And then this line is a camera position. I think I'm going to have to explain how I calculate where to put these, but I'll do that later after I explain everything else. So now, since everything is calculated in terms of 3 dimensions, and we don't have 3-dimensional computer screens yet, I had to project or somehow convert from 3 dimensions into 2 dimensions. And those 2-dimensional coordinates are precisely screen X and screen Y. Screen because it will be projected or displayed onto the computer screen. This line sets the color. It seems to be white. The thing with the GPDraw file, every time you draw on it, it doesn't erase previous draws, and I could not find a clear method that would clear the canvas. So what I had to do was I went over everything in white instead. And so that would essentially be erasing the whole thing because the background is white. So this is calculated in much the same way as the following loop, which is almost the exact same, except I do not re-increment theta. So now this is the actual drawing part, which is what you actually see. I increment theta by 0.1 radians. That's about a reasonable number of degrees. I'm not sure how many. So here, this is so these lines add, or rather replace, the points in that array I created, and I put in the coordinates of the 4 hydrogen atoms. And so then I'll explain what all this means later.
Yeah, explain to us how you got to those formulas.
Okay, so So to calculate this, one needs to know that in a regular tetrahedron or tetrahedral shape formed by methane, the angle between two hydrogens and the carbon is 109.5 degrees. So then, will it show up?
Sure, absolutely.
Okay.
Thank you.
Let's see. So imagine if this was flat and you had this hydrogen coming out here and the other hydrogen going into the wall. If this was 109.5, then so if I let this be the y-axis and this be the x-axis, then this would be that minus 90. That would be 19.5 degrees, which I obviously have to convert to radians, which is why you see small numbers here. But I'll work in degrees because it's easier. So 19.5, and I assigned each length to be one unit, so that the distance between carbon and hydrogen was precisely 1. So then notice that since it's rotating about the y-axis right here, then these y coordinates will remain the same. You can imagine this going in a circular pattern on the plane, like so. So then the y-coordinate will be constant for each, and it's exactly why you don't see theta in any of these values. And I'm going to explain what negative 1/3 is. So since this length is 1, then this length right here would be the sine of 19.5, which is 1/3, and negative b because it's below the y-axis. So then to calculate the x position is slightly more complicated. I'm going to look at it from a different perspective. So this is the x-axis, this is the z-axis, and the y-axis is coming out straight out or straight into the wall. Bad calibrated. So by symmetry, you know that each of the hydrogens, and here's the carbon in the middle, you know that each of these angles is 120 degrees, which, if I'm correct, would be 2.09 radians, I think. So I let theta be equal to this angle right here, and then I can easily compute this angle right there, theta 2, and then I can compute this angle, theta 3, by just simply adding on 120 and 240 degrees.
So you need to know what theta, theta 2, and theta 3 are at every instant of this molecule.
Right.
Okay.
But if we know theta, we know the other two as well.
And theta is incrementing, so it keeps rotating.
Yes. So, so then if we want to compute the x and z coordinates, we're going to need to use this theta right here, which I already talked about, and this length. However, since these molecules are not precisely on the xz plane, they're actually behind it, if forward is positive, then they're actually behind it, so this length is somewhat less than 1. Apparently, it appears to be less than 1, and
That's actually an optical illusion.
yes,
Okay.
it's actually 1 degree, but it is out of the board. So, what is that value? Well, to do that, you can just use this view again, and you see that it would be the cosine of 19.5 degrees, and that would be 0.94281.
Wow.
So that's this length, appears to be 0.94281, and from there we can use sine and cosine of theta in order to compute its x coordinates and its y coordinates, the z coordinates, I'm sorry.
And what is, can you just put on the board there, for those that may want to study later on, some more advanced trigonometry, what is the relationship that exists between x, y, how far it goes into or out of the plane of the board, and theta. What are the relationships?
Well,
In other words, what are the relationships between rectangular and polar coordinates, right?
yeah. So I should cover that. So if you have a point x, y in the, or maybe x, y, and z in the three-dimensional plane, so the length or the magnitude we say is square root x squared plus y squared plus z squared, but it doesn't matter. It's basically if we have a point, it would be the distance from that point to the origin, and
Right.
that right there is what is the magnitude, which I'm going to say is r. So we can write that in a different form as r, something along these lines. You can represent it as a form of angles. Like, for example, when you project it onto this plane, that plane, and this plane forward, you get three angles: alpha, beta, gamma. It's pretty weird how that works, but this one is a bit simpler in that the y-axis, the y-coordinates are all the same, and that you know that the magnitude of these x projections are always going to be the same. Because this magnitude is the same, this one's the same, so this length, which is that one, would also be the same.
That's right. So in this program, the actual distances between the molecules, between the atoms of hydrogen and carbon, those distances don't vary. They're the same.
They're all, yeah.
Although in real life, those distances would vary.
Slightly, but
Okay.
yes, I set them
And in
arbitrarily.
order to project them onto a two-dimensional surface, now that you have the coordinates, you use your camera angle and
Yes,
then calculate the
that's-
distance between that and each of the points.
Right, and that's
Yeah, right.
that's another thing that I'm going to explain. So now I have how to compute where exactly.
Can you erase all of that?
Yeah.
And then use the board again.
Yeah.
This is not working. The instant it touches the block.
So that's how I calculate each of the actual positions. And so now to actually convert them into two-dimensionals is something maybe a bit simpler. So let me explain how that works. So I have the x, y, and z here. So let's say I have a point.
This is a different angle now because before you were talking about the y-axis going into the plane of the board. Now you're doing z.
Right.
Okay.
I'm going to set this point, just for example, to be 1/2, negative 1/2, and it's positive, and 1/2. So this is a positive z right here, positive x right here, and positive y. So it's below the plane. And so now what I do to actually convert these into two dimensions is I have two different objects, but not in the computer science sense. I have two mathematical objects here. I have a plane, which represents the screen, and that's the equation z equals 1. And then I have a point, which I have defined
Camera angle.
up here as 0 to 2. So it's actually right here, 0 to 2. And this is the camera. So what I do in order to convert these into two dimensions is I draw a line from the point that I wish to convert and connect it to the camera and find where that line intersects the plane, z equals 1. And that's the point which I display. So it obviously depends on the camera, the plane, and the point, but for these purposes I have the plane and the camera fixed. So how to actually compute those is slightly complicated, but not.
Show us where in the code you do that.
Yeah, and those are these lines here. these are the formulas which do that, and I'm going to explain these formulas right here. So the equation of a line in three dimensions requires a fourth parameter t. If you want let's say this is Vx, Vy, and Vz, x, Vy, Vz, and this point right here in general is x, y, and z, x, y, z. Then the equation of a line that passes precisely through these 2 points, depending on a fourth parameter t, would be x. Can I calibrate this?
Okay, pause it. Pause the screen.
Yeah. So the equation would be x, y, z. These are using points or vectors plus t. There's our fourth parameter. Vx minus x, Vy minus y, Vz minus z. And this makes a bit of sense because it's essentially we're starting off at a point and then we're going some multiple of the difference between the two. So it does make sense.
It's similar to the slope-intercept form of a line?
Yeah, exactly. Or the point-slope form.
Point-slope, sorry.
This is almost exactly the point-slope form, but in 3 dimensions. And so you can indeed verify that it does indeed pass through these 2 points with t equals 1 and t equals 2. T is our fourth parameter.
So at the point where it touches the screen, z would equal 0.
1. I set the plane to z equals 1.
Oh, right.
Because...
Why did you set it equal to 1 instead of 0?
Well, the number 1 is rather simple, number 1. And the other thing is, none of the points, when they're rotating, will actually strike the point z equals 1. And I was worried there might be some complications. There probably aren't, but it might. So it's probably better to stay clear of something that might not work.
Right.
Like I could have arbitrarily done 5, but 1 works fine.
Okay.
So to compute when z equals 1, we had to find where the z component is 1. And so that would be z plus t times z equals 1, or whatever I set the plane to. And then you find t equals z minus 1 over z minus vz, just reversing it. And then you can plug this in to find the x and y coordinates. And that's rather straightforward, and that's that would be what these lines are. You can see there's vz minus 1, or wait a minute. Oh yeah, a bit more algebra to clean it up, I guess.
Okay, pause the thing. You can just briefly discuss the math, but you don't have to do any more math. I'd rather you focus now on the actual lines of code.
Okay. So you can compute the x and y coordinates using this value of t we've calculated by setting the z coordinate to 1. So now for the rest of the lines of the code, you will notice that when the program was running, let me show you something. Let me show you what it looked like. When it was running, you'll notice that the atoms, number 1, they were filled in, but number 2, they weren't 100% filled in. How I did that effect, or did that, I did it like so. What I did, here's what I calculated before, as I just showed you. And then this would be the color yellow. So what I did was I made 4 circles of radius 4, 3, 2, and 1, emanating with the center at that point which I calculated, which essentially would look something like this, and like that, essentially filling in the circle. However, of course, because we are working with pixels and integers, it's not 100% filled in, but it's the best I can do at this point. What I have here, that's black. So what I did was, this sets it to black right here, and then what I do is I draw a circle around it, radius 5, which is the border of it.
Just let me interrupt you real quickly, Faraz. For those of you that may not be familiar with when you're talking about RGB values, 000 is black, 255, 255 is white. and then you have all different colors in between. You have a red component that goes from 0 to 255, a green from 0 to 255, and a blue from 0 to 255. All right, continue.
So this right here, that's 0, 0, 0 as translated into my two-dimensional coordinates. It's the same as over here. I'm not going to go through that. Whoa. And so then what I do is, you notice there's a blue part, and I haven't really done anything blue yet. That would be this part. I draw the central carbon atom last, outside of the loop, which goes through the 4 hydrogen atoms. This is the 0, 0, 0, as I mentioned earlier. And I have, this is the blue color, and I change the pencil's color to blue, and I draw a fill-in, or try to fill in the circle of radius 7. So it is bigger than the hydrogen atoms, as carbon is, in fact, larger than hydrogen.
And then why do you put sleep 100?
Sleep 100 is just so that it gives a gap and it doesn't rotate too fast. Because the thing is, in between drawing, every single line or every single command that draws, for example, these, and these, by the way the GPDraw works, it does a small gap in time unless you do no delay. But if you were to do that, it would rotate much too fast to be of any aesthetic pleasure.
Okay, can you run it one more time, just setting VX, VZ equal to 1.
VZ
Yeah.
equal to 1, that's the camera position. So
exactly, just set it equal to 1.
If
I
you
know
set
it's
it
I know it's at 2 right now. If you set it equal to 1,
would that give you any errors?
I think so.
Compile it and see.
Yeah, it would give you 0. So let's see what happens when we do that. I've been avoiding this, but I will be glad to do that.
You haven't changed the variable, it might come out and bite.
There you go. That's what it looks like.
Ah,
It doesn't work.
So the mathematics doesn't work at that point.
The math should work. It just gives you 0, and then Vx would be the same the whole time.
Faraz, change that back to the way it was, but make thread.sleep 0 instead of 100.
Okay.
I want to see that. See what would happen. It probably look like a molecule that's going berserk, right?
Yeah. There. That's what it looks like.
That looks
It does rotate slightly, but not very much.
doesn't look as you had the way you had it before, it's better.
Yeah.
Yeah.
Hence why I put that in there.
Because all the arms are the same length.
Yeah.
Well, actually, you're
No, that's
talking
where it
about
comes down
the
to that
distance between the hydrogen and the carbon.
Are
All
they?
those hydrogens,
Are
yeah,
they
they're
same?
the same.
It's equal
It's just
length.
that it's an
Because
illusion.
it's 3D, right, I understand.
Yeah.
I understand.
And that's the program.
But actually it looks better this way.
Can we see without it erasing anything? Just the underlying structure?
Yeah, sure. It looks terrible, but I will do that.
So is he gonna get an A100 for this or what?
Yeah, it's an outstanding presentation.
So this is what it looks like.
Wait, it didn't do anything.
Whoops.
Yeah, they didn't
There you go.
Hey, by the way, there is a wood stock. Close to the-
There you go. That's what it
Oh,
looks
wow.
like.
Wow, that's awesome.
It looks like a.
So that's the increment of
like a peanut
0.1.
there.
Yes.
0.1 radius.
Wow, interesting.
I
Yes.
like that.
And after a while, it just turned to a black.
Yeah, the inside will turn black, but the outside
Go
will
back
stay
to your
yellow.
code for us.
Yes.
I noticed, scroll all the way up. I noticed that you've got the public static void main throws exception.
Right. I discussed that. That's because of the thread.sleep.
Okay.
It throws some form of exception, something to do with interrupted, when the thread becomes interrupted. I don't really like try-catch statements, so it's just as valid to do throws exception instead.
Okay.
I could have done a try-catch statement, but I think it's rather anomalous and unusual.
Right.
Look, he doesn't want mundane frivolities.
Yes.
involved in the work.
There you go. Questions or comments, gentlemen?
Good evening.
Very good for us.